Hello to everyone, myself Sridhar Reddy Monte, a lecturer in ECE from Government Institute of Electronics, Secunderabad. So, today we are going to learn the C18 scheme, Electronics and Video Engineering branch. Subject code is 305C and subject name is Network Analysis. So, we already in Chapter-6, that is Network Theorems and Resonance, and a few topics which are covered in my previous video. So these are the few topics which are covered in my previous part. So once again we go through review of previous topics, then we will start today lecture. So first of all, in the last class we discussed about the maximum power transfer theorem. It is for DC circuits and AC circuits. First we learned the statement for DC circuits, and we also did prove the maximum power theorem statement. And here the statement is nothing but the here maximum power theorem states that from the source the maximum amount of energy or power that can be transferred from the source to the load when the load resistance is exactly equals to the source impedance, then under this case only the maximum amount of power that can be delivered to the load. So also we did proof for this statement, we did, and this is in the case of DC circuits. In the case of AC circuits, the statement is different here. It states that the maximum amount of power that can be delivered to the load when the load impedance is equals to the complex conjugate of the source impedance, that is ZL equals to ZS star. So under that condition only maximum amount of energy that can be transferred to the load. And also we did here prove for this statement, this maximum power theorem for AC circuits are classified into under three different cases. This is the first case, and similarly we have two more cases in the maximum power transfer theorem. And also we discussed about the steps to apply maximum power transfer theorem for a given network, and also we did some problems on maximum power transfer theorem. So these are the topics which are covered in my previous part. Now in today's video, in this lecture we are going to learn reciprocity theorem, and here proof of reciprocity theorem, and also we are going to do some problems on reciprocity theorem. So here coming to the statement of the reciprocity theorem, here this theorem permits us to transfer source from one position in the circuit to the another circuit, So coming to the statement, the theorem states that in any linear bilateral network, the ratio of excitation and response is constant even when the excitation and response are interchanged. It means the source to the excitation to the response is constant when their positions are interchanged in a linear bilateral active network. So this is the statement of our reciprocity theorem. Coming to the explanation, here consider the network shown in figure here 6.9a. So they are given one network like this. So V is the voltage introduced in the loop 1. So this V is nothing but source voltage, and while the current in loop 2, here we are interested about the current in the loop 2, and the ratio of this source voltage to the response, this current, we are taken as one quantity. And according to the reciprocity theorem, it states that the ratio of here the source voltage to the response in the second loop V by I remains the same if the positions of our V and I are interchanged in the same network. Means now I am going to replace here the source position is here and the response position is here. Now I am going to interchange. First I am going to find the ratio of these two quantities, that is V by I in the first case, and I am making it as equation 1. And in the second case I am going to replace the positions here. So the source, in the place of source here I am going to take the response. So that's why if you observe here, in the first loop I am going to find the response, and in the place of response I am going to replace the source here. So here I am connected a source in the second loop. So when these two positions are interchanged, in the second case, if I find the again source and response ratio, then I will get the same value, that is V by I. Then it is called the reciprocity theorem is proved. Here, in other words, here V and I are initially mutually transferable, and the ratio V and V by I is also called as transfer impedance, denoted as Z12, where V is the voltage introduced in loop 1 and I is the response due to V in loop 2. So now V is the voltage introduced in the loop 1 and I is nothing but here the response introduced due to this source voltage in loop 2. So that's the meaning of this sentence, and V by E generally is also called as here transfer impedance. So this is about the statement and the explanation. Now we will discuss in detail with the proof. So here now I am going to prove these statements with the same example here. Before interchange, first initial condition, I am going to find the source excitation to the response. The other name for the excitation is nothing but source. The other name here response here is nothing but here I am going to find the current. Consider a circuit like this. Let us consider a network having single voltage source in the first mesh as shown in figure A. So assume a circuit like this. Let the currents in the first and second loops or meshes, we are assuming it as I1 and I2 respectively. Now we are interested about the response here. I due to the current, due to the voltage source here, V means we are going to find the ratio of this V by I by using any network simplification methods. Here I am using mesh analysis to obtain these currents I1 and I2. From I2 I am going to find the response, this is I. See here, in the step 1 I am going to obtain the set of two loop current equations by applying KVL to each loop. We already know that, we already studied here. The KVL is nothing but sum of potential losses equals to sum of potential drops in a closed loop. If you observe here, there are two drops are presented here and one source is presented. The source we are written here and the two drops are here written as Z here. The first drop is going to be across Z1, the second drop is going to be across Z3. So the drop across the first element Z1 is nothing but the amount of current which is flowing through Z1 is I1. So that this Z1 into I1, otherwise you can write these drops in the right hand side, because KVL is nothing but sum of potential is equals to sum of potential drops. Generally, potential rise is nothing but number of sources presented in the loop. Only one source is presented. We should write it as in the left side. Number of drops generally indicated in the right side. So drop is going to be presented across here the passive components. That is in resistor, inductor, capacitor are impedances. There are two impedances presented in the loop 1. So the drop across the first loop 1, the first element Z1 is Z1 into the current, and the drop across the second element Z3 is, there are two currents are flowing which are flowing in opposite direction through the Z3. So the total resultant current which is flowing through the Z3 is I1 minus I2. Why we are assuming the I1 minus I2? Because we are writing KVL expression for loop 1 by assuming the loop current I1 is greater than I2, and minus sign is we are getting here due to the both the currents which are flowing opposite to each other. So that's why I1 minus I2 into Z3. Generally we can also take this into the right hand side. So finally we will get here, after rearranging all these terms, finally we will get V equals to Z1 plus Z3 into I1 minus Z3 into I2. So this is about the loop 1. Now come to the loop 2 here. In the loop 2, apply the KVL here. KVL is nothing but sum of potential rises equals to sum of potential drops. There are no rises are presented, so that's why I am writing here 0. There are 2 drops are presented because there are 2 passive elements are presented in the loop 2. So this is the Z2 is the first passive element and Z3 is the second passive element. The drop across the first passive element Z2 in loop 2 is equals to the amount of current which is flowing through the Z2 is I2. So this I2 into Z2 will give the drop across the first element in loop 2. The drop across the second element, that is Z3, here is given by Z3 into, here there are again 2 currents flowing through the Z3, I2 and I1, and both are in opposite with each other. So the resultant current is I2 minus I1 into Z3. So already we discussed all these things in our mesh analysis concept in chapter 2. So after simplifying these expressions, finally we will get here loop 2 expression as minus Z3 into I1 plus Z2 plus Z3 into I2 equals to 0. So this is about the equation 2 for loop 2. I hope everybody understood how we got these expressions loop from KVL. So in the mesh analysis, by applying KVL to the loop 1 and loop 2, we got these expressions, equation 1 and equation 2 for loop 1 and loop 2. Now we got the expressions. By using those expressions, I am going to write it in matrix form, that is Z into I equals to V. So the Z is generally, there are 2 loops are presented, then it will become 2 cross 2 matrix. So there are 2 unknown currents and this is the here, so voltage matrix. Now from the equation 1 and 2, I am going to place the elements. So finally I will get Z11 as Z1 plus Z3, Z12 as minus Z3, Z21 as minus Z3, Z22 as Z2 plus Z3, I1, I2, and these are obtained from equation 1 and equation 2 right hand side terms, V and 0. Now according to the Cramer's rule, now I am going to find the I1 and I required only I2. So the general formula for I2 by using Cramer's rule, because we need the response. Here the response is going to be presented in loop 2. So the current through loop 2 here is generally is given in the diagram as I2. This I2 is same as I. So that's why. So here we are interested about only I2 current. So I2 current is nothing but the general expression is delta 2 by delta Z. So first we should find the delta Z, then after delta 2, then substituting delta 2 by delta Z. So how to find this delta Z and delta 2 values, those are given in step 3. So delta Z is nothing but determinant of Z matrix. This is the Z matrix. We already know that. We solved so many problems on this concept in mesh analysis. So after finding delta Z expression, that is Z1 Z2 plus Z1 Z3 plus Z2 Z3. Now similarly find the delta 2. Delta 2, how to obtain delta 2? By replacing this V matrix in the second column of our Z matrix. Finally we obtain delta 2 value, that is VZ3. Now substitute delta 2 and delta Z values. Just now we got here. Now delta 2 is nothing but VZ3 and delta Z is nothing but this is the one, and after substitution here we obtain I2 value or I value as this. Now from this I want the according to the statement here reciprocity statement, that is source to the excitation. The ratio of source to the excitation we should find. So now we substitute V and substitute I value. Just now we got it from here. After substituting and rearranging, finally we will get excitation to the response equals to some constant. Here the constant value should be, we got from the network as Z1 Z2 plus Z1 Z3 plus Z3 Z2 by Z3. So this is the expression for the excitation to the source, excitation to the response ratio. We got it under case 1. Now I am going to interchange the places of source and response here. After that should be taken in the case 2. After interchange the position of source and response. If you observe the diagrams here, the source is presented in loop 1. Now I am going to replace this source place into the response place. That is, here I am going to replace the source, and this here this response I am taken in the loop 1. After drawing the circuit here, if you observe here, again considering the network which is after replacing source and excitations. Now I am assuming the current through the loops are I1 dash and I2 dash in the case 2. Here both are flowing in clockwise direction. I am assuming here. Now here the direction we are not going to change. If you observe the response is going to be flowing in downwards. So that's why I am going to take it here downwards response direction, and also the source direction also I am not going to change. If you observe here, the source is going to be presented in the upwards. Here also I am going to consider it as upward direction. So the directions we are not going to change. Just we are replacing the positions or places of source and responses. Now same way I am going to obtain the set of here there are two loops are presented. Now I am going to find these two currents by using mesh analysis. So if I am going for getting I1 and I1 dash and I2 dash currents, here I am applying KVL for the two loops. So the after applying the KVL to the first loop, we will get here expression as Z1 in plus Z3 into I1 dash minus Z3 into I2 dash equals to 0. So this is the expression for here loop 1. Similarly, the loop 2 expression, we already know that how to write these expressions. So that's why I am directly explaining the concept here only. So after writing KVL here for the loop 2, that is sum of potential rises equals to potential drops. So after substituting rises and drops values, finally we will get expression as minus Z3 into I dash plus Z2 Z3 into I2 dash equals to minus C. So this is the expression for, this is the next expression, this is for loop 2. After getting loop 2 and loop 1 expressions, we are going to arrange them in matrix form. So finally we got the matrix form, that is Z into I equals to V. So by using Cramer's rule, I am going to find the unknown response here. Generally the response is presented in loop 1, means we are interested only about I dash. If I know the I1 dash value, that is exactly same as I value, but it is flowing in opposite direction, means I is nothing but minus I dash 1 or I1 dash we should consider. So that is the thing, and that is the difference between the case 1 and case 2. So here we are interested about I dash or I or I dash equals to, we should take as minus sign here, minus delta 1 dash by delta Z dash. Here from here we should first we should find the delta 1 dash by delta Z dash. So delta 1 dash and delta Z dash we have taken here. So after substituting and here simplifying these expressions, finally we will get here I1 equals to, or I equals to response minus here Z3, we should consider this V into Z3 by Z1 plus Z1 Z2 plus Z1 Z3 plus Z3 and Z2. So this is the expression for response. Now I am going to substitute in the ratio, that is source and excitation ratio after substituting these two values in the place of I. If I substitute this value, finally we will get this ratio as Z1 Z2 plus Z1 Z3 plus Z2 Z3 by Z3. I am assuming this is equation 6. If you consider the source and response ratio in first case, that is before interchanging the position of source and response, the ratio we got here in the form of expression 3, see here, and it is equal to the after replacing the source and response positions of places, we got here the expression as 6. If you closely observe the equation 3 and equation 6, both are same, means according to the reciprocity theorem, the ratio of response, source and source to the response should be constant even when the positions are interchanged. Hence, according to the statement, we proved that statement, and hence the reciprocity theorem statement is proved. So this is the way we should prove the theorem statement. I hope everybody understood these things, the reciprocity theorem statement and explanation and proof. I hope everybody understood. If everybody understood, then we will go for problems. Here, by using the reciprocity theorem concept, we are going to solve some simple problems. Consider the example 1. For easy understanding, and initially I am considering a DC circuit. So if you observe my every video, first I will start with the simple problems, then I will going to increase the complexity of the problem. So in the same fashion, for this theorem also applied here. In the first example, I am taking a simple problem that is going to be built with DC circuits. So in the example 1, verify the reciprocity theorem for the network shown in below figure. This is a given network. So if you observe this network, how to prove reciprocity theorem means the ratio of, we know the statement of the reciprocity theorem, that is ratio of source to the response. Where we are going to find the response here? Across the C and D elements, across the C and D points, one resistor is presented. So through the resistor we are going to find the current, means the response is nothing but here the current through this 2 ohm resistor presented between C and D points. Means according to the reciprocity theorem, the ratio of source to the response, means the current through the 2 ohm resistor should be constant when these two positions are going to be interchanged. So means this concept is going to be adapted for this problem in the solution. So I am considering this problem in two cases. So in the case 1, before interchange, means we are keeping the positions of the source and response as is. Now I know the source value, that is 20 volts. Now I am going to find the response, means the current through the 2 ohm resistor. Now I am going to find. So by using any one of the network simplification methods, I am going to find this response, that is current through the 2 ohm resistor presented between the C and D elements. So for that, I am considering step 1, select the mesh currents as shown in figure, means I am applying here mesh analysis to find the unknown current, that is I. So there are 3 loops are presented in the circuit. I am assuming there are 3 currents are presented in the 3 loops, I1, I2, I3, all are flowing in clockwise direction. I am assuming. So the current through the 2 ohm resistor generally equals to the I3 current. Means if I know the I3 current value, then I can easily find the I value, because I3 is exactly equals to the I value. So this I3 value or I3 current, unknown current, I am going to find out with the help of mesh analysis and Cramer's rule. So here, according to the inspection method, mesh current analysis inspection method, I have written this matrix form, that is Z into I equals to V. Z into I equals to V means there are 3 loops are presented. So there are 3 unknown quantities unknown currents are presented, and the order of Z matrix is 3 cross 3. There are 3 unknown currents, that is, the size of the matrix is 3 into 1, and this is the V matrix, it is also 3 cross 1. So this Z matrix we are going to find by using inspection method. That is, there are total 9 elements are presented in the Z matrix: Z11, Z12, Z13, Z21, Z22, Z23, Z13, Z31, Z22, Z32, Z33. So these are unknown quantities I am going to find with the help of inspection method. If you observe this problem, first initially we are going to find the first row of Z matrix. The first element is Z11. Z11 is nothing but self-impedance of loop 1. Otherwise, it is also called as sum of all impedances presented in loop 1. Means, if this is the loop 1, sum means how many impedances are presented here. There are 2 impedances, that is 2 and 3. Take the sum, we will get here 5. So that's the way we should find. Similarly, Z12. Z12 is nothing but it is the mutual impedance or transfer impedance between loop 1 and loop 2. So this is the loop 1, this is the loop 2. Between these two, only one impedance is connected, that is 3 ohm, and the sign of this impedance should be depends on the direction of these two currents. If both are flowing in the same direction, we should consider plus sign for this impedance. If both are flowing in the opposite direction, we should consider the sign for here negative. Both are flowing here in the given diagram, both are flowing in opposite, so that's why they are considered minus sign here. And Z13 means it is the mutual impedance between loop 1 and loop 3. So there is no mutual impedance presented between loop 1 and loop 3. So that's why we are taken as 0. Here in the solution we are taken as 0. And similarly Z21 equals to Z12. So directly this value are taken here. This is Z22. Z22 is nothing but it is the self-impedance or total impedance of loop 2 or summation of all impedances presented in loop 2. There are 3 impedances presented in loop 2. I am going to add these 3. 2 plus 2, 4 plus 3, 7. We should consider positive sign for this diagonal elements Z matrix, and this value is Z23. Z23 is nothing but mutual impedance between loop 2 and loop 3, and this is only 2 ohm resistor is presented, and here the sign for this 2 ohm should be negative because I2 and I3 are flowing in opposite direction. So minus 2. Similarly, Z31 is nothing but 1, 3. So directly I have written here. Z32 is nothing but Z23. So directly I have written here. So this is the Z33 is nothing but self impedance of loop 3. So there are 2 impedances presented in loop 3. That is 2 plus 2. We should consider 4. The sign should be positive always for a diagonal matrix of the diagonal elements of the Z matrix. So the unknown currents are I1, I2, I3, and V matrix are nothing but V1, V2, V3. V1, V2, V3 is nothing but here V1. How to find V1? V1 is nothing but the total sum of sources presented in loop 1. Only one source is presented in loop 1, that is 20 volts. So directly I have written here. Here V2 is nothing but observe this loop 2. How many sources are presented in loop 2? No source. So that's why I taken 0. Similarly, no source is presented in loop 3. So that's why this is loop 1 source. This is no loop 2 sources are presented and no loop 3 sources are presented. That's why I considered 0, 0. So from this, we are interested about only I3 current. Because I3 is same as I current. So this I3 I am going to find here. I3 or Ix or I equals to delta 3 by delta Z according to the Cramer's rule. Now first I am going to find delta Z and delta 3 values. So delta Z is nothing but this is the mod of Z, delta Z matrix here. Here after finding delta Z value here we are getting it as 84. Similarly delta 3 is nothing but after replacing the third column in here in the Z matrix, we are going to find the determinant of the third here. So finally we got here the determinant of 3 equals to 120. Now I know the value of delta 3 and delta Z. Substituted. Finally I got I3 current as 143 amps. So this is exactly equals to the response value, that is unknown current, that is the current flowing through the 2 ohm resistor. Now I know the source value and response value. Now that ratio should be that ratio we should take as here 20 by 1.43. 20 divided by 1.3 we should consider as equation 1. Similarly, now I am going to change the positions of source and responses in case 2. In case if you observe the case 2, I am going to, after interchange. After interchanging means I am going to interchanging the position of the voltage source and currents in figure C. If you observe figure C and figure B or figure A, first initially the source is presented here, response we are going to find out here. Now I am going to replace this source with response here. I am going to find the response in this loop, in this branch, and I am going to connect this source here. So means after interchanging source and response values, now I am going to find the response value, because I know already the source value, that is 20 volts. Now again I am going to find this I value with the help of mesh current analysis. So because there are 3 loops are presented, by assuming 3 currents in each loop, that is I1, I2, I3. Now I am going to find this response value using mesh analysis. If I know the I1 current, then that is exactly equals to the response in the second case. So this I1 I am going to find with the help of the same concept, that is mesh current analysis inspection method. We already know how to write these things. So that is Z into I equals to V. Just now we discussed how to write Z matrix, I matrix and V matrix. So from that we are interested about I1 current only. So that I1 current we are get it as the formula for I1 from Cramer's rule is delta 1 by delta Z. So delta 1 and delta Z just now we solved here 84 for delta Z, 120 for delta 1. After substituting the Ix value we will get it as 143. The source and response values, that is V by I, that is again the same as we got here, 20 by 1.43 in case 2. Similarly in case 1 also we got here 20 by 1.43. Both are equal. So in the both the cases current value and the response values are same, and hence the ratio should be constant. Hence the reciprocity theorem is going to be verified. I hope everybody understood the concept. So in the first case we should keep the source and response values positions same as, and we should find the response value, and after that we should find the ratio, that is source and response, treated as expression 1. After interchanging source and response values, we know already source value, we should find the response in case 2. After finding response, again take the ratio, that is the source and response, then consider as expression 2. If expression 1 equals to expression 2, then the reciprocity theorem statement is going to be verified. I hope everybody understood this concept. Now this is in the case of DC circuit. Let us discuss some more problems on AC circuits. So if you observe this here, example 2 now we are discussed with AC circuit. Okay. Now consider the example 2. So this example 2 is taken on AC circuits. So here first read the example. Find the voltage Vx in the circuit shown in figure 2a and verify the reciprocity theorem. They given one AC circuit like this. So instead of giving voltage source in the previous problem, the source value they are given as here voltage source. Now we are considering in here an AC source, that is the current. Here the given the source value as current, that is 5 at an angle 90 degrees amperes, and we are going to find the response, that is the voltage across the minus J2 ohm capacitor. Now we are going to find. So means here the source to the excitation here, now we are going to find here. So in the case, so that can be solved by in two cases. That is in case 1, before interchange here. Before interchange means if the diagram is considered as same as, now I am going to find the response here, that is Vx value I am going to find. So Vx value I am going to find with the help of current division. Means here a current is started from the source, that current traveled up to here. At this point, the current having two paths, means the current is going to be divided into two currents, that is I1 and I2 currents. So we are interested about only I2 current, which is flowing through the minus J2 ohm capacitor. So means if I know the current through this I2, this minus J2 ohm branch, that is I2. So by using that I2, I am going to find this Vx. That is, V is nothing but that I2 current into minus J2 ohm will gives the voltage across this capacitor, that is Vx. So that's why. So in the step 1, initially I am going to find, I am assuming this current is going to be divided into I1 and I2 in two branches. So we are interested about I2 current. So I2 current is nothing but the total input current, that is this 5 into at an angle 90 degrees into the opposite impedance. Here we are interested about to find the current in the second branch means. So the opposite impedance for the second branch is 5 plus J5 divided by the sum of two impedances, that is Z1 and Z2, 5 plus J5 plus 2 minus J2. So after minimizing and substituting all the values, so finally I will get I2 equals to minus 1.725 plus J 4.31 amps. So generally this expression is mentioned in the form of rectangular. Now I am going to convert it into polar. So that is 4.64 at an angle 111.8 degrees amperes. So this is the amount of current which is flowing through this branch. So I know the current which is flowing through this minus J2 ohm reactance. So if now I know the then we can easily find this Vx value here. So the voltage across minus J2 ohm is given as Vx equals to the amount of current which is flowing through that element and its impedance, that is I2 into minus J2. Now just now we calculated I2 4.64 at an angle of 111.8 degrees into here we are converted this impedance in polar form, that is 2 into at an angle minus 90. After multiplying these two terms, finally we got here Vx equals to 9.28 at an angle 21.8 degree volts. Now I know the source and response values. So consider that ratio, assume that ratio as equation 1. Now in the case 2, now interchanging the positions of voltage source and current source and response. See here, now I am going to interchanging the positions of the response and current source. So generally response is going to be presented in here. Now I am going to connect here source value, that is this is connected here, and this voltage is going to be, I am going to find out across 5 plus J5. So the figure exactly get converted into figure B. So the response, the source is flowing through this branch, and the current we are going to find the response across 5 plus J5 ohm impedance. Now the same way the current initial input current started from here, it will reaches up to here. At this point this current is divided into two currents because there are two parallel branches are presented. So current is divided into I1 and I2. So we are interested about I2 current. If I know the I2 current, then I can easily find this Vx value. Means first initially I am going to find the I2 current by using current division rule. After that I am going to find this Vx value. So according to the current division rule, the current flowing through the 5 plus J5 ohm resistor is given by that I2 current is equals to the total input current into opposite resistance. Opposite resistance, if you observe the diagram, for this branch, all these three elements are connected in series. So for these three elements, the opposite is going to be minus J2. So minus J2 by the total impedance of the circuit. So are two parallel branches. This is the total impedance of two parallel branches. So I substituted this input current and these two values and minimizing this expression or simplifying. So finally I got here I2 current equals to 1.31 at an angle of minus 23.2 degrees amperes. So now I know the current which is flowing through the 5 plus J5 ohm impedance. So if I know the current flowing through the impedance, then I can easily find the response of here, that is voltage. The voltage is given by the amount of current and its impedance value. So the voltage drop across this 5 plus J5 is given by Vx equals to the amount of current which is flowing through the 5 plus J5, that is I2, into branch impedance, that is 5 plus J5. After substituting I2 and impedance values, so finally we got here Vx as 8.6 plus J3.44. Now if you observe here, this Vx we finally get 9.28 at an angle of 21.8 degrees volts. So in the case 1, here they are not taking the ratio, just they are by using response only. They concluded whether both are satisfied the reciprocity theorem or not. If the responses are same values, then they concluded that because the source value never changes, the response values we are getting same value in case 1 and case 2. So then they concluded that the response is same, then the ratio values automatically going to be constant or equal, because the source value is not going to be changes in case 1 or case 2. So therefore with that they are concluded, hence the reciprocity theorem is going to be verified. So with this, so I hope everybody understood this concept. The problem 2 here, they initially they gave one current source, they asked us to find the response, that is voltage across minus J2. So this can be solved with the help of current division rule. First we found the current through the element, and then by using that current we calculated the Vx. So we taken the ratio, that is voltage and source and response ratio, and assuming equation 1 in case 1, that is in before interchanging. Now after interchanging, here the positions of source and responses, again I am calculated the voltage, that is response across 5 plus J5 Vx. So here after getting same by applying current division rule, to get the current through that element. After finding the current, we have got the voltage across that element. Now in both the cases the response is same. So with that they concluded here the reciprocity theorem is going to be verified. I hope everybody understood today's concepts. So that is reciprocity theorem, and its first we discussed about the statement and explanation, and here proof also we calculated, we did its proof by using that concept. Here we applied that concept to the two examples, that is one for example 1 is for DC circuit and example 2 is on AC circuits. I hope everybody understood today's lecture. Thank you. Thank you for watching today class.